Okay, welcome back. Let's start again. Okay, just to make sure that the organization-wise we are well on track. So there were two working groups this morning where so I had one where we sort of went through the exercises. They are not mandatory. So if you think you have understood the stuff, you simply don't come. You don't have to come. It's an opportunity for you to go through the exam material in a quiet way. So to me that worked okay, I think. I don't know about the other group. If you have suggestions, if this worked out with Denise, that you had the time and got the feedback that you needed. Otherwise, let me know, let her know. Let's see how things go. Programming-wise, I saw that up to now there were relatively few people with technical questions who registered with the sheets with Jeffrey and Paul. Is that because you couldn't find the spreadsheet where to put your group's name in, or is that because you didn't have problems? Did anybody have a problem but didn't find the sheet? Okay. So the way we're organizing this is that we have booked these slots for the practical. They are usually not that big, the practical rooms, and they are in principle reserved for us. So you could be able to go there, and there will always be one of either Paul or Jeffrey, depending on if there's really the slots are fully booked. Then both of them will probably be there. But if there's not that many slots, only one of them will be there. You can work there, and if you have immediate questions and they are free, you can always ask questions. So that's the setup. But if you have a specific question, prepare it well, use your slot, and try to solve it. If this is something which we can't solve in these 10 minutes, then you can always talk to these guys and say, do you have time at other spots? So Paul has more time, Jeffrey is pretty busy, apart from these slots where he will be in the lab, but Paul has more time. You can then make individual appointments if you have a specific technical problem that is really so difficult to solve that you can't do it in these 10-minute slots. So you should get help, sufficient help with the practical stuff. Yeah, so if there are problems, let me know, let Jeffrey know, Paul know, or about the working groups. There's one working group at 1:30, there's one working group at 4:30 today, and 2 tomorrow, so where hopefully you can practice all the stuff. So my timing was rather bad, so I've only got to part 2 of the lectures, and there are 4, so we have to speed up a bit. This is sort of the classic AI algorithm, and that is A star. It's the idea of it is I think reapplied in many systems and so forth. So it's something you should have seen. It's not that relevant for our adversarial search, but it's a nice algorithm anyway. So you have to know it, and you have to also be able to apply it and maybe reproduce it in the exam. So remember, we had now the tree search where we put the nodes that we still had to evaluate in the fringe. And in the uninformed search, we just did this in a more or less random way. Whenever we had children that we needed to evaluate, we put them in the fringe. And then we had the fringe was either a stack or a queue, and depending on that, we would just get an order of search. But obviously, mostly we know more about these states so that we can say, okay, this state is probably better than the other one. So the decision which we take where we, in chess, give away our queen for nothing, we all know that this is a bad decision. So let's put it at the very, very end of the queue, and only evaluated if all other things have failed. So using heuristic information is very important in helping us managing the huge information. And that's how we get from the uninformed tree search to the informed tree search, where we have an ordering of the elements in the queue that is according to a quality that we have heuristically evaluated. And we discussed the different features of these possible heuristics. But one thing we didn't do is to slightly get away from this greedy approach, where the greedy approach is to only look at how close am I from the goal. So in each of the steps of the search, the only information that I take into account is a heuristics that tells me it's that far to the goal. And that often helps find a solution fast, but it doesn't help you always find the best solution. So what we have to do is, in the best first search, not only greedily look at the distance to the goal, but also what costs do I have already had for doing the search to get to this specific moment in my search. And that basically means that we split the evaluation function into two parts. We use it's usually the f of n is the evaluation function of the quality of a node by which we order it in the fringe. And we split it into parts of a g, which is the path that we have already, the cost that we have already taken to the goal, to the state we are in. And h is the heuristics that we had used before in a greedy way, that is a distance from the state we're searching in to the goal. So basically we get extra information, namely the one that we have already spent on the way. And that is this g function. So g is the cost so far to reach the node, and h is the estimate, the heuristic value that we have estimations to get to the goal. And that together estimates the total cost of the path through n to the goal. And now this is not greedy anymore in the sense of the definition of the word, because we not only look at how far are we to the goal, but it also looks how much do we have already spent for a certain node, how costly was it to get there. And whenever you use an evaluation function to order your nodes in the fringe that is based on g and h, then this is called an A algorithm. Don't ask me why it's called A. That's the sort of the property of a best first algorithm that takes into account the heuristics to the goal, but also the costs to get to this state. And then A star is a subset of A, so it's an algorithm that has specific special properties on the heuristic itself. And that means that A star is the same, is this best first search algorithm with G and H, with one specific condition, and that is that the heuristic is admissible. So what does that mean? The heuristics is admissible if it never overestimates the cost to reach the goal. That's all. So formally, if we know the true cost, which is this H star to get from a node to the goal, then my estimation is always smaller than this value. Smaller or equal, yeah. Okay, that's all there is to the definition of the A star algorithm. And if you look at the example, then I think this becomes clear how you have to read this. So remember the example of getting from Arad to Timisoara, for example. Timisoara, or let's say Bucharest, because we want to have the... And then I know that the real way I have to take in my road will do this, yeah? The heuristics that we use in order to estimate the shortest path to go from Arad to Bucharest was the B-line distance. So this is the shortest direct distance between these two places. It's by definition that this B-line distance is defined as the shortest way between A and B, 2 points. So the line between the 2 points. So this means that whenever we take this B-line distance, it will be smaller than the real value which is exactly what is required for the heuristics to be admissible. Yeah? So this is how this looks. If we apply this, we know that we have this estimation, these estimations of the distance between the cities and Bucharest. And we know that if you travel by road or by whatever way, it will always be bigger. It will take longer than the B-line distance, longer or equal, but it will only take equal if you take the B-line distance, because that's the definition of the B-line distance. So we know that the heuristics up here, the heuristics H is an admissible heuristics. Okay, so now how does the A star algorithm, because now it has been promoted from an A to an A star algorithm, how does it work? It basically looks at the state Arad, where we start, and it calculates F. What is F of Arad? Anybody? Oh. So F of Arad is defined as G of Arad plus H of Arad. What's G of Arad? The path until now. So what is the cost of how long have I traveled to get to Arad from Arad? 0. And what is H of Arad? 366. So basically, we have now in our fringe, we have Arad 366. So F of Arad. Yeah. Okay, what are the successes? We have Timisoara. What's the F of Timisoara?
It's 188, 118 plus 329.
CBU. What is F of CBU? You get the general picture. And we have to do Zerint, which is again, you always calculate the F value, then you order the nodes by the F value, and you explore the one with the smallest value. Yeah? And then for the rest, you simply do the standard best first search, because it's a standard depth first search approach, where we now, the only difference is that here for Arad, we are not taking only the distance directly, but we also take the distance that it has already traveled the way. And this makes a difference when you go from Sibiu to Bucharest, because if you remember, I told you that if we do the standard best first search, the greedy approach, we find the Sibiu to Făgăraș, because Făgăraș is closer to Bucharest than Râmnicu Vâlcea. So we find the path Sibiu, Făgăraș, Bucharest, but if we would have gone this way, it would have been shorter. So now let's look whether our algorithm will really make this difference. So let's now look at the task to get from CBU to, so G of CBU is 0 is now the assumption. So what would be F of Făgăraș is 99 plus 176. The F of Râmnicu Vâlcea is 80 plus 193, which gives us 5, 275, and 372. Yeah? So this one is smaller. Yeah? So we explore this one first. Yeah, sorry?
F also got us as F of CU minus 99.
Say it again. Why would you want that?
Just asking if it's possible.
According to my algebra knowledge, that should be possible, but I don't think it's very useful or sensible. Anyway, let's take this offline because we need to calculate now the children of Rimni Kuviljeja, and that is f of Pitesi, which is g, the distance we have traveled according to our knowledge in the search to here. How much is that? Does it sound reasonable? When I start at CPU, I go to Rimku Vijaya, and then I go to Pripesi. I have first 80 kilometers, and then I have 97 kilometers, according to this map at least, which is 80 plus 97 is 177. Yeah? Then I still have to add the g, so that's only the g. I still have to add the h. So h of Pitesi is 100. So that the f value for Pitesi is 277. Yes? No. I sort of missed the step where I said, let's start at CBU. So this is where I said we look at the reduced task of going from CBU to Bucharest. Yeah? We always start from the one that is the closest according to the f value. So we reorder our sets according to the f value. So we started with S, CBU, which had the distance was 253. So we've done that, we've covered this. And then we go through it through the order of the f values. Now the bad news is that we have explored Pitesi, but we haven't explored Fagaras yet. So we have to do that.
Because Fagaras appears cheaper at the moment.
Fagaras appears cheaper at the moment than this one. But then we look at Sorry, I don't get it. Oh yeah, sorry. No, sorry, I should have done those as well. Forgot, no, Kralova. So now you look at the f value according to this path to Bucharest, which is g, don't forget, it's g plus h. So this is now, these 99 plus the 211 is 310 plus 0 is still 310 is bigger than this one. So we explore Pitesi again. And now we get the path, the f of this, by this path is now 80, 97 plus 101, and that is smaller. So we get this path. If I play music during the lectures, you are also allowed probably. So this was smaller. I forgot so it's 80, 278. So basically, the algorithm will determine this path instead of the other one, which is the optimal one, which is the shortest path. Yeah. Okay. Look at this algorithm. The only idea that you need to really understand is that this is a simple best first search. You always put the things in the fringe in the order of f where f is the sum of g and h, and g is the path that you have taken, and h is the estimation of the distance to the goal. And it is complete. It is exponential with a path length, so it's pretty bad, but that's how it is. It's really complex, but it gives you the optimal solution. Okay. Now we spend more time on informed search, and this is really sort of one of the classical algorithms. If you read about AI in the last century, then the A-star algorithm has always played an important role. So you need to be able to understand what it is and how it works. This information now, in the third part, is more for your interest in entertainment. I think it's quite relevant to the project that we have, because I want to first talk a little bit about multiplayer. That's less relevant because there is also a version of Schnapsen with 4 players, which is really nice. Is a really nice game to play, and 66 I played when I was young. Then you have 4 players, and that basically changes the dynamics completely. Bridge is also a very interesting object of study for these kind of games where you have 4 players, they collaborate. So it's interesting to think about how this works. And the basic idea is that the min-max algorithm would work in exactly the same way if you have more players. So here's the assumption that we have 3 players that play each for their own game. And basically what you do in each of the moves, you calculate the same values for who would win. So you don't have a single value anymore, but you calculate the value for player 1, for player 2, for player 3, and then you would basically allow you to choose. He would be allowed to choose this game situation because this is where his value is optimized. So the idea is exactly the same, but everybody would not only maximize or minimize one single value, but you would try to optimize your value in a vector. For the rest, the algorithm would work in exactly the same way. A different thing that is obviously in these game scenarios interesting to take into account is the element of chance. Don't confuse this with what we have in Schnapsen. There is an element of chance in Schnapsen at stage 1. At the very beginning, the cards are shuffled and distributed. From the moment that had happened, there is no element of chance anymore. There is an element of uncertainty and imperfection of the information that we have. It's an imperfect information game, but it's not a probabilistic game. Because there are no sort of, it's a deterministic game. Every step has only one follow-up step. And that is different from the elements of chance, where you don't know before what happens. The approach is very similar, but conceptually it's different. So if you look at a game of backgammon, are there any backgammon players here in the room? Yes? So I probably explained it completely wrong because it was 20 years ago that I played last time. So basically you have to move your stones from one part of the board to the other part of the board, and you throw dice. I think you throw 2 dice, and you can then distribute the number of points that you get over the movements of the stones. Is that, correct me if I'm wrong? Yeah? Sort of right. So there is the element of chance that when we throw the dice, we could get any answer, any number of points between 2 and 12. Yeah? If both dice have a 1, then we get a 2. And if both have a 6, then we get a 12. And depending on the numbers, there is a certain probability attached. So the 2 only occurs 1 out of, how many? 18? How many? 36. The 7 occurs most often, I think. 3 plus 4, 2 plus 5, 1 plus 6. So there is the chance that this happens is bigger. So basically what you have is in the max move, you you start with the probability that a certain event happens. And I will talk more about probabilities next Friday, but you understand enough that we have different situations, different states that we could end up with, depending on a certain probability. And if you attach a probability value to each of those states, you can make an estimation of which is the best node, the node is with the highest chance of you winning. And that's sort of the simple combination that you do between the simple min-max algorithm together with a weighting by the probability that an event will happen. So this is an example of this node where you look for a certain position that you would come in, and you could make your moves. Depending on whether you do a 1 and a 2, then you have a chance of 1 of 18, because you have 36 different options if you throw with the dice, and you make your in your terminal decision, you can then build up the value for your estimation of the quality of the move according to the game itself, plus the chance that this event will happen or not. So you can't calculate the definite min-max value, but some estimation according to the weighting with probabilities. And that basically works with that at the node you can really calculate the full game, because at each stage you know exactly the depth, because at each state you throw the dice, you have only one state to go to then once the dice is thrown. So you get to some winning or losing position, and then can backpropagate, but it's always weighted by some expected min, by some chance, by some element of chance. Because here you have the probability for each of the nodes you have in the calculation of the value. So basically it's the same idea. The only thing is that now you need to check for every possible state in the uncertainty space. You have to take it into account when you calculate the value of the tree. Now we get to what usually was the beginning of the course. So I'm sort of starting now with the introduction to rational agents, intelligent agents. What on earth are we doing here in the first place? Maybe you've asked yourself that question, maybe not. I'm now trying to give you the remaining 10 minutes, 12 minutes, some ideas about what are we, intelligent agents, intelligent systems, what are we talking about? So to me, and I think many people, intelligent systems is a subfield of AI, which is really about building the AI. So AI is a broader field. AI also has elements of cognitive psychology, where you really, or neurology, where you try to understand how the intelligence works in humans, what that means to translate it to people. So there is I don't know whether it exists still, but there is a sort of cognitive AI approaches. We are a computer science department, so this is really a course of how can we build a system, something that we can program, something that sort of gets alive and takes some decision and does some machine intelligence. Obviously now comes the question, what is intelligence? And we've, you have made already some points, and I'm not going to give an answer on that. There have been, particularly in the early years as well, but it's still ongoing. There is a huge philosophical discussion. What does it mean? Is it really related to humans? Can other things be intelligent? I think the case is proven that they can. There is this. There were attempts by Turing, for example, who tried to come up with a functional definition. So can we prove that something is, even if we don't really know what intelligence means, if we don't want to commit to something, can we have a check? Can we define intelligence? And we came up with this Turing test where you would put a machine and a human in the room, and whether you can find out that communicating with this machine or the human, who of them is the machine and who is the human. This was one way of operationalizing the definition of intelligence, which was an interesting one. It was often tried, and I think it is now more or less solved. it has a flaw. It has a big flaw because it says it defines intelligence in terms of human capabilities. And maybe something can be even far more intelligent than a human. Maybe someone finds out that it's a machine because it's far more intelligent than the human. Is that then a good definition for intelligence? I don't know. But these were operationalizations in the early years of AI. What we really try here in this course is to reduce more to the notion of rationality. So we're trying to build rational artificial agents. And a rational agent is something that chooses actions according to some idea of I want to achieve a goal as well as possible. Doesn't mean that it necessarily knows everything about the world, but it's about this optimization towards some goals it formalizes and it sets itself and it tries to achieve those goals. That's the notion of rationality, and that's the notion that we apply here also for the intelligent systems, the intelligence in the intelligent systems. So let's start from this notion of rational agents. What is it we build? So you build a Schnapsen program, you write a little bit of code, and we take the grandeur of calling this an intelligent agent. Is it an intelligent agent? What do we mean by this in the first place? And there are 4 elements that we need to discuss here and to see how this is. What is an agent in the first place, and what is sort of the types that they could have? What is then a notion of rationality that would work for those agents? And what is the role of the environment that they function in? And let's have a quick look at those terms before we end this week, or at least the new material for this first week. So the agents, in principle, is a very, very loose notion that I would apply, and that is an agent is anything that has some contact with an environment through perception, and maybe can perform some actions by some actuators. That is a very, very loose definition, very weak definition of an agent, because it also would, for example, apply to the heating system here. So there's no intelligence yet. It sort of measures that the temperature has risen to a certain level, and then it lowers the functioning of the heating system. So this would be an example for an automated agent. It takes some interaction with the environment, the world. It makes some decisions, and it then acts upon those decisions. And we can abstract over those systems. We can basically write a function, an agent function. What does it do? It takes as input some sequence of percepts and outputs an action. And then we can program a program that executes this function, and we can run it on some physical architecture. So there are 3 different things. We have the functionality that we can describe mathematically. We have the code that executes it, and we have a box that does it. And then the rationality comes in when the things become more intelligent. If you have a notion of what is it I want to achieve. So my heating system starts having a notion, there is a certain level of agreeability and a temperature that I want to achieve. How can I do this? What is the actions that I need to take into account? So there's we need a tiny little bit of rationality starting in the system, where you have a decision making that if it is above 21 degrees, then stop heating. So this doesn't mean rationality that I know everything or that I have the perfect thing. So it's already good enough, and it's more realistic in real life, that you perform according to certain standards, according to your expectations that you define yourself. The quality of the functioning of such an agent depends very strongly on the kind of environment that they perform in. So this agent performs in an extremely simple, it might be complex, but for his task, it's very simple. It's just measure temperature and take a decision. But this is for the kind of things that we are now starting to build, where we really see some more intelligence in the rationality. That is an important thing to take into account, namely, what kind of environment does it perform in? Where does it do it, our agent? What is it supposed to do? How can it do it? Because what can it know from the world? And what can it do in terms of its actuators that it has? And this is sort of something one should always take into account when building an intelligent agent. What is the performance, what's the environment, what's the actuators, and the sensors that it has. So if you look at it, the idea of I want a fully automatic taxi that can drive from A to B, and the task is to get me from the airport to the hotel as quickly as possible. There is some things it has to do. It has to be able to drive, it has to be able to be safe at a certain destination. Maybe it has to make a profit if you want to. Maybe it should be run legally, it should be comfortable, whatever. So there is some sort of performance criteria. And then the question is, where does it perform its actions? And that would be the streets or on a railway, whatever. So, and in this environment, it has to take care of everything that comes along. So it has to take care of pedestrians, it has to take care of the other traffic. If it's snow, it should be aware of it, and so forth. What can you do with this taxi? You can drive, you can brake, you can horn, you have speakers, display, whatever. And the senses you get is video, sonar, speedometers, engine, sonar, whatever you have in these tools. So if we now talk about an intelligent system such as a self-driving car, this is exactly the kind of things that the people who build them have to be fully aware of. Then there are different types of environments that we have to take care of, and that's the ones that I've been talking about quite often now. So that's the question of observability, deterministic, static, discrete, and single agent. And for examples here, we have the game of solitary, where you can play cards with yourself. It's a single player game. Backgammon, internet shopping, you want to find somewhere on the web, you find the best offer for a thing you want to buy, and the self-driving car. Observability, we have seen that with Schnapsen. The question is whether you have access to all the information that you need. And if you look at this example in solitary, this is really a perfect information game. You can observe all the cards, I believe. Backgammon is also fully observable, and the other ones are. So this is a kind of analysis that you should do again and again and again for our application, and I've rushed a bit through that for our Schnapsen example. Deterministic means that whenever you take an action, it's clear in which situation you get. So this is in each of the stages, I know which the next state will be. So that's the difference between the backgammon, where you at the next stage there will be a probability, there will be a stochastic decision taken. So backgammon is not a deterministic game, and neither is driving a car, for example, because you never know how the environment might change. Changing the environment is an important one. So if suddenly you would play with a different deck of cards in Schnapsen, then you should really change your algorithms. The ones that we have wouldn't work on those. So our algorithms only work for very specific environments, and that's something we have to be aware all the time. I will skip this in the interest of time. And you obviously have the single agent paradigm that backgammon. You have someone who tries to beat you in internet shopping. Someone else might want the same product at the same moment and pays a better price if you're at an auction or something like this. And the taxi, of course, you have all the children running in the way of the automatic car that we have to take care of and that we have to be aware of. So I think the Schnapsen types would be not fully observable, partially observability, well deterministic. So if I play a card, then the game engine knows exactly at which new state it is. So there's only one, every action gets me from one state to another one. It's static. There is no sort of let's change the cards and give us a new deck. It's discrete, so there's only one step at a time. There is no sort of rational number lottery in the middle. And it's not a single agent, as we all know, because we have an adversary. And this creates a space of complexity of problems. So we have very simple AI problems that are fully observable, deterministic, episodic, static, discrete, and single agent. And even those can be very complicated. So if the search space is huge, so I think chess is more or less,
except the single agent part.
Apart from the single agent part, it has 2 players. But for the rest, it's this very simple environment. Whereas driving the car through the streets of Amsterdam automatically by speech or whatever is a completely different kind of game in terms of the intelligence that the system needs. This means that we also need to look at different types of agents. So the one I talked about in the wall has a simple set of rules, and it fires its actions whenever certain criteria are fulfilled. So you have the environment, you have the agent, you only look at the moment. What is the world right now? It's a stateless representation. It just looks at the world right now. It has a set of conditioned action rules. It applies them. If the temperature is lower than 22, do this. So it's an agent, a simple reflex agent, not very intelligent, but already sort of a beginning.
Uli would be one of those, I think. Uli would be one of those.
Yeah.
He's pretty reflexive because he has really well-defined rules of what to do what.
Exactly. So the bully bot would be exactly an example for this. It's a very simple pseudocode that you can look in here. More interesting ones are the agents that have a notion of a state. They know what happens with the world and how some input changes this reflection of the world in the states. So this then might still end up in some decision making by applying some rules, but it takes into account far more, for example, the history and so forth. So I guess, but we are still working on this, that next week the bots that you might build on the basis of some human knowledge might be far more on this level, that you know what has happened in the game, what is a bit of the environment, and then you fire certain rules. Okay, in this situation it's better to play the king rather than the queen. And these kind of decisions, they can be seen in terms of this reflexive state agents. What this game has already, of course, the Schnapps game has this notion of a goal, so the notion of rationality. We always play with the goal of being as effective, as winning, as quickly as possible, as comprehensively as possible, and so forth. So there is more than just knowing about the state and a goal. It really, you're performing towards an objective, and this really, I think, makes you rational. And this is, I think, a huge step. And then the last one, which is the one that we are going to address in the third week, is that you don't do the same mistakes again, and that you also learn from the experience and behavior of others. And that makes the agent then adaptive and a learning agent. So I have about 25 seconds left to talk about AI research. The good news is there is no more slide after this. The point now is that I think you should all in the next days more or less get up and running with your bots for the practical assignment. But now the question is, why do things happen? So it's this sort of curiosity that I think we as university researchers, students should have. Why on earth is this thing performing better than the other? And not only let's fix this, we're not on the fixing side of life. It's not about building the thing that performs best here. It's about understanding why a certain thing works better than another. So if you come up with the slowest bot ever that loses all the time, but you can explain why this is better than having the best bot, and you just say, oh, it's some magic. Yeah? So what we are going to do the next 3 weeks until the end of this course is that we start this engineering work that we have now getting into a research work. Why on earth is in this relatively simple but already quite complex environment, one method working better than another one. And this is hopefully some way of thinking that you apply in the next days when you suffer with the code, that you always think this is understanding about how these intelligent systems methods work and perform in maybe on different examples later, but in real life. Thank you.